Measures of variation. The first of such measure is the range, and the range is the difference between the maximum data value and the minimum data value. Or another way to express it as a formula, the range is the maximum minus the minimum. Only the maximum and minimum are used, so the range is very sensitive to outliers, and so it is not resistant. The range does not truly reflect the variation among all of the data values, however, due to the fact it only uses the maximum and the minimum. An example of this is where we take the range of the first 5 pulse rates for males from the dataset 1BIASED dataset, from the numbers 84, 74, 50, 60, and 52. The maximum is 84. Minimum is 50, so the range is 84 minus 50, or 34.0 beats per minute. The standard deviation for sample values is denoted by a lowercase s. It is a measure of how much data values deviate from the mean. The population standard deviation, on the other hand, is denoted by a Greek symbol sigma. The formula for the sample standard deviation takes the square root of the sum of all of the deviations around the mean squared divided by n minus 1. Or we could slightly rewrite that as n times the sum of all the values of the variable squared minus the sum of all the values of the variable squared divided by n times n minus 1. The standard deviation can never be negative, but it could be 0 if all the data values are the same. Larger standard deviations indicate greater amounts of variation. The standard deviation can increase dramatically from outliers, and as such it is not resistant. The units of measurement are the same as those for the original dataset, and the sample standard deviation is a biased estimator of population standard deviation sigma. The values of S do not center around the population standard deviation sigma. My next example has us calculating the standard deviation of the first 5 pulse rates for males from the dataset 1 by dataset of 84, 74, 50, 60, and 52. If we throw it into that sample standard deviation formula, that being this formula, so the square root of the deviations around the mean squared, and you want to sum all those, divided by n minus 1. If you put all those inside of there and calculate that standard deviation, you get a value of 14.6 beats per minute for the sample standard deviation. The range rule of thumb is based on the principle that the vast majority, or 95%, of sample values lie within 2 standard deviations of the mean. It uses the population mean mu and population standard deviation sigma. For large representative samples, we could substitute x bar and s for the mean and standard deviation respectively. We could also estimate s by taking the range divided by 4, and that'll be the approximation for that sample standard deviation. Significantly low values are the mean mu minus 2 times sigma or lower. Significantly high values are the mu plus 2 sigma or higher. The values that are not significant are between those two values, so between mu minus 2 sigma and mu plus 2 sigma, as you can see from the graph down here. If we want to use the 153 pulse rates of males from the body data dataset 1, the mean is x bars 69.6 beats per minute, and the standard deviation is s is equal to 11.3 beats per minute. Assuming this is a large and representative sample, use the range rule of thumb to find the limits separating values that are significantly low or significantly high. Then determine whether a male pulse rate of 100 beats per minute is significantly high. So we are using x bar plus and minus 2 times the standard deviation s. So 69.6 minus 2 times 11.3, that's 47.0. And 69.6 plus 2 times 11.3 is 92.2. So significantly low is less than 47 beats per minute, and significantly high is more than 92.2 beats per minute. A pulse rate of 100, though, 100 is greater than 92.2. So the pulse rate of 100 beats per minute is significantly high. And we want to use the range rule of thumb to estimate the standard deviation of the sample of 153 pulse rates of males listed in the dataset 1 body data dataset. From this 153 values, they have a minimum of 40 beats per minute and a maximum of 104 beats per minute. So the range will be 104 minus 40 divided by 4 for this approximation. This gives us about 16.0 beats per minute as a representation, or an approximation I should say, of the sample standard deviation. Now the population standard deviation, on the other hand, the population standard deviation is a slightly different formula, and it is also rarely calculated, but it's still useful to at least know the differences. The population standard deviation sigma is equal to the square root of the sum of all of the data values minus the mean squared, and that will be then divided by the population size capital N. So do know the difference between this and the sample standard deviation. The variance of a sample and of the population, this equals the square of the standard deviation. So for a sample variance is s squared and population variance is sigma squared. The units are the squares of the units of the original data value, which is why this is very rarely calculated. The value can increase dramatically from outliers, so it is not resistant. The sample variance s squared is an unbiased estimator of the population variance sigma squared. The sample standard deviation s is a biased estimator, however, of the population standard deviation sigma. The value is never negative, only 0 if the data values are the same. And I should probably note also while talking about this, this is also in reference to the fact that for the value is never negative, only 0 is the data values are the same. That is also because of when we take the deviations around the mean and we add all them, since we have both positive and negative values, this value becomes 0. So the reason why it's never negative is because we have to square. We have to square those deviations if I don't accidentally write the wrong thing on there while talking. We take the value, each data value, subtract the mean, and square each of those values, and then add them up. Then that should not equal 0 at all, unless again the values are the same. The mean absolute deviation is a simple calculation. It's not used in inferential methods and is rarely, if ever, seen. But the mean absolute deviation is the sum of all the deviations about the mean and the absolute value of all those deviations about the mean. So it's never negative. Divided by the sample size n. Now, why on earth do we divide by n-1 in the standard deviation formula? The n-1 are the degrees of freedom in the sample standard deviation. That's where only n-1 of the data values can be any possible value. Since the sum of the deviations is 0, right, as we saw, we add up all those deviations. Since we have positive and negative values, adding all those up makes 0. The last term must be the one that causes that sum of deviations to actually be 0, which is why we have n minus 1 degrees of freedom. The sample variance centers around the population variance. So the sample variance, for the most part, pretty much underestimates the population variance. The coefficient of variation describes the standard deviation relative to the mean expressed as a percent. So both of these have the same idea. They take the standard deviation divided by the mean times 100. So for the sample coefficient of variation, this would be sample standard deviation divided by sample mean times 100%. For the population coefficient of variation, that will be the population standard deviation sigma divided by the population mean mu times 100%. And both of those are rounded to 1 decimal place. So for example, using the 153 pulse rates of males from the body data dataset 1, the mean is x bar is 69.6 beats per minute, and the standard deviation is s is 11.3 beats per minute. For their heights, x bar is 174.12 centimeters, and the sample standard deviation s is 7.10 centimeters. We want to compare the variation of the pulse rates and the heights. So for the pulse rates, we take 11.3, the standard deviation, divided by the mean 69.6 times 100%. This makes about 16.2%. And for the heights, the standard deviation is 7.10 divided by the mean of 174.12 times 100%. This makes about 4.1%. So due to this, we could see that these pulse rates here, they have a much higher variation than the heights. And when it comes to these estimators, we didn't know about biased versus unbiased estimators. A biased estimator is where the value of the sample, an example of that, I should say, is where the values of the sample standard deviation do not tend to center around the value of the population standard deviation. For the most part, the sample standard deviation tends to underestimate the population standard deviation due to the division by the degree of freedom of n-1. The unbiased estimator, this is where the values, for example, of the sample variance tend to center around the value of the population variance, instead of overestimating or underestimating the population variance. Thank you.